So it's good to have a little audience. Thank you. Today we're going to talk about the problem of index entry locks that we fancily subtitled The Curse of the Phantom Keys. You know, just to attract people to our conference. Quick word on who we are, where we come from. So, we both come from the company Proginov. We are an ERP publisher, so we develop our own solution and we deploy it for our customers. We also propose a hosting solution. We have 2 data centers on site, so we can provide in a SaaS-like service for our customers. We are established, well, I wasn't there obviously, at that time, since 1996 near Nantes, and we now have a staff of more than 300 people. And the funny fact, Patrice likes to brag about this, we have more than 14,000 databases in production. OpenEdge databases. Right, so for some of you, you may not know Nantes. So just a quick postcard about Nantes. So Nantes is located in on the west coast of France, near the west coast of France. So you have the usual landmarks, the pretty castle when Brittany was an independent duchy. It was not part of France yet. You may recognize, yes, so Nantes was the hometown of famous writer Jules Verne. You may have heard about him. And more recently, you can find, maybe you've heard of them, the machines, the animal machines in Nantes. And for those of you who, like me, like music with heavy guitars, we also have a very famous festival called the Hellfest that takes place not very far from Nantes. So next year in June, if you want to have your tickets, just please do. And well, just for reference, this is a picture of one of our first barbecues this year. So we do a couple when the weather gets better around May. So yeah, just to add a little bit of context. So I am Paul Murgues. I have graduated in 2013 at the University of Southampton. So I did no computer science at all until I entered Proginov to develop in OpenEdge. And since then, I got interested in software performance, and now I am trainer in software performance for the new developers that come in regularly in our company. And I'll let you introduce yourself.
Yes, I'm Patrice. I'm working on Progress since 2001. I started working on optimization in 2005 and joined Proginov 3 years after, and I'm a DBA since 2010. Okay. So, we are speaking about the index entry lock. I'll explain you what are we talking about, where do they come from, when do they appear, how are they eliminated, how to measure them, and why should we bother about them.
So first, what are we talking about? So, disclaimer before that, we will be talking about index entry locks, placeholders, dead keys, deleted keys. That's all those words for the same concept. So I will use them interchangeably. So what are we talking about exactly? So during a transaction, obviously at every moment in a transaction you need to be able to roll back to the previous state. So the tables that are equipped with a unique index leave a placeholder at the position where the record is, so that the value is not taken by another transaction that would create a record. That's all fine. The only problem is that at the end of the transaction, the placeholder is not removed. It stays there. Only if the index is unique. But the placeholder stays there practically forever if you don't do anything about it.
Okay. Then when do they appear? The first thing, it's when we do record deletion. On this example, I will sum some of the pure line records by item name. So I will create 100 records, and on the first part, and in the second part, I will delete 90 records to sum them on the item names. So at the end of this, I have created 100 records, deleted 90 records, but I still have 10 records, but 100 index keys. So there is 90 index keys on the DB.
Another similar example, when you are renumbering the lines in an order, if you have a unique index for these lines, so you affect a new number to these lines and you reorder them. So in our example, we have created 50 records and we have done 2 renumberings. So in the end, we have 50 records, but we have 100 keys in our index.
Okay, last example is a rollback. We are creating 50 records. Doing the rollback, at the end we have 0 records, but we'll still have the index. It's like this.
So there is a mechanism inside progress databases that deal with these placeholders. So when you add a new entry in your index, if there is one block that is completely filled with placeholders, it gets recycled to the free chain, but only if it's 100% deleted keys. So RM chain, free chain, I'm explaining that just in a moment. So what are we talking about exactly? So that is the outputs of a DB analysis. And here you can see that you have 40 blocks that are linked to this index. Here you have 11 blocks in the delete chain, so that's the RM chain, it's the same. And you have 20 blocks in the free chain. So what happens is when you have a block that is completely filled with deleted keys, it goes to the RM chain, so it's like it's been flagged to be recycled at any moment. And when you have an event like creation of a new key, one block is recycled to the free chain and can be filled again with new keys. So if there is such a mechanism, why should we bother? Well, it only works if new keys are created. That's the first limitation. So after you have deleted massive amounts of data and you haven't created enough data, so you have a lot of those blocks in your RM chain and they take space. Another case that happens is that when you delete a lot of data but not contiguously in this index, you only need one valid key in a block to be kept so that the block is kept in the standard chain and is not recycled. So you could have potentially a whole index with 99% of dead keys, but they won't be recycled at any point. So the consequences are obviously on the volume taken by the index and on reading performance. When you do a for each on the table, you read a lot of, well, phantom data. Sorry.
So, okay, so we'll do a little digression. At Progenov, we have tools which help us to do DBA tasks like profilers. We have health check monitoring, quality supervisors. We are using 3 releases of Progress, 10, 11, and 12. So when we are working on OpenEdge 12, we can't write our data in a DB OpenEdge 10. So we have to duplicate our DB, and we have a process which automatically copy every update on one DB to the other DB. So from moving the data from a DB in OpenEdge 11, we are using CDC, so CDC change tracking, and the CDC tables help us to target the records to move. And when we want to move some data from OpenEdge 10 to OpenEdge 11, we are using the audit feature. So by using this, we are doing a lot of creation on this table and a lot of deletion also. So one of these cases is on the profiler. My colleagues are doing some measurement every day, between 2 and 10 measurements, but there is a lot of time between them. So one guy will do a measurement. It's create a lot of line in the profilers. These lines are transferred to the other DB with the CDC, and we delete the CDC records. But during all the time before the next measurement, our process which copies the data will read the index on Twiloc time to time to time, without finding any record, but it's reading a lot of indexed key. One other example, it's on our health check monitoring console. So it's not the same activity. We have more than 300,000 CDC change tracking created and deleted every hour. So there is a lot of creation. So the standard process on the ERM chain is doing a lot of activity. But the unique index on CDC change tracking is the table number and the change sequence. So when we are working on one tables, the tables after the index key or the tables after are protected by the first table. Due to your queue process, we have some delay of few seconds, but it still have some keys which are protected, and we are reading this key time to time to time.
So is there Anthony Cross here?
No. So it's one example on our health check monitoring console. So you can see I'm doing a lot of DB access, 18 million of records, but I'm only read 600,000 of records, 20 million of DB access opposed to 600,000 table suites. And when I go to my global view of my process, you can see I'm reading this number of this index, which is quite huge, opposed to the tables. So I'm reading one tables for 30 index. It's only index and Twilocs, which I'm reading. So it's cost a lot for us.
So now that we know what we are talking about, let's do a little experiment. So we have a better view of how to approach the problem. So we have a model database with a table, a unique index on the table, and a second index that is a copy of the first one, except that it's not unique. We load the table with 350 million records, and then we duplicate the database and we do purges, but obviously non-contiguous purges. So we need to the number of records to go down by 10, 20, 40, and 60%, and then I'll show you the results. So you can see on the left-hand side that the number of records has gone down, obviously. But on the unique index, you won't see any difference. It still takes up the same amount of gigabytes, still the same number of blocks, it's still the same level, and it's still the same utility percentage. For comparison, if you do the same thing with the same index but not unique, you will have roughly, well, you will have the same number of blocks, but what difference will be is that it's the utility percentage that will go down. You will have blocks with a very small amount of keys. And when you redo an IDX build with the recommended factor of 86, you will see your number of blocks obviously going down, but here the interesting thing is that we have earned a level of index. So that can be, is it 10, 20%
Yes,
increase in read speed? So it's not negligible.
Okay, so these ghosts are more frequently on ODBs than we could think before. Adam, you speak about IDX compact. Yes, it's what I did every day. So we have more than around 6,000 DB, which have at least one index with more than 200 blocks. And we perform around 1,700 IDX compact for those DB. And we compacted 5,000 index during May. And we are doing, like you said, several DB analyses, one every week. So we are compacting more and more. So we have done something like 20,000 IDX compact. What is surprising, it's we are doing them in 80% of the case because of index on lock, and a little bit more because there is an insufficient percentage util on this index. So we are compacting a lot of case because there is placeholder on the DB.
Right, so still you, sorry.
That's me again. So we have to estimate them. So to estimate them, I did a little process working on spot 2000 dB. It was on other line. Yes. So I have at starting point, I have a certain amount of records with their size, the index, number of blocks in the index, the index size, and the percentage util. I did 2 IDX compact, and as you can see, there is not really, there is a difference between the number of blocks and the size of the index, so it decreases a lot. After this, I create a certain amount of other line, deleting the same number, but it's not a contiguous deletion. So at this time, you can see that the index increases in size. And I have always the same percentage util. And doing IDX compact at this time did not change anything. I have the same value. Yes. After this, I get almost all the records and create 1 million of records with a bad percentage util. So my number of blocks increase, and which could be surprising. the size, yes, in the index block size, oh, there is something wrong. I think it's above, it would be 16 million there. No, it's 11 million. It's the size decrease, the number of index increase, and the percentage util decrease. And at the last step, I'm deleting a few number of records and creating, no, only deleting. And you can see there is no difference on the number of blocks, the size of the index, and its percentage util. So it's what we're analyzing.
So first method to measure the percentage of index entry logs, the simplest one, well, simple and dirty, you just do a for each on the index, and you measure, you read on the VSTs your stats. So you compare your table reads and your index reads. So in our case, it's 801,000 versus 1,201,001 reads. So it's a ratio of about 33%. Second method, you will need an analysis tool called IDX block report. So the output is a file looking like that. So you have a description of every block in your index. You have the types, what are on which level are the blocks, so are they root, non-leaf, or leaf, and the utility percentage. So here you can see, for example, that there has been a recent split on this block. And you have the levels and the number of entries. So what we can learn from that, we can combine this, the IDX block report and the DB analysis to find our numbers. So we can calculate the number of blocks that are 100% composed of index entry logs by taking the number of index blocks from the DB analysis and the number of blocks that have at least one active key from the IDX block report. And if we take the number of records from the DB analysis and the number of leaves in IDX block report, we can have the number of index entry logs in the blocks that are not 100% index entry logs. So if we do the numbers, we find the same 33%. I hope I was clear.
Yes. But on previous release of OpenEdge, there is an issue on index block report. Sometimes you will find less leaf than records, which is impossible, just impossible. So we have to find one trick to find what is the percentage of placeholder. So what we imagine is to find the best value for what we call the number of index in a block which is 100% filled by an index. So to calculate them, we use this. Depending on the number of records with the number of index block reports with the percentage util, it gave us this value. We store all the results of our DB analysis, so we can find which is the highest value. This is this one. So it will be the target, the reference for us. By this value, we compare for the new DB analysis, and we have 33% of error. Okay, so this is the results for the different step, different method. So for the first, we have around 25%, around 0, again around 25%, and each time we have a very close value for each of our meters. So we have the choice.
So now we know they're here. How to get rid of them? Obviously, for copyright reasons, I could not use the actual logo, but you know what I'm talking about. So we have seen in the introduction that we could use the internal mechanism of progress databases of recycling blocks from the RM chain to the free chain. So we could just create new keys, and for one dummy key, you can remove a whole block of phantom keys. So that's one way. You could push it a little further, so you can do you can create a few records there, and you undo the transaction in the end. So you can see that you have created a few extra keys, but you have removed, well, a maximum number of the number of keys that you have added. Here we have added 4 new keys, but only 3 blocks were available for recycling. So it has its limitation, but you could imagine when you have a process of mass deletion, in the end of a cluster of deletion, you could add a few extra keys, do a rollback, and you basically remove the blocks on the RM chain that you just created.
Okay, so move back to my profiler. I made process for transferring data from CDC to my DB on OpenH 10. What I have to use is this. I just adding this. It's for example on profiler on the line of the profiler. I'm create this on this DB, which automatically creates CDC change tracking record and CDC tables, which delete one ERIM block on the 3 tables. And it decreases the read of the future read on these entry logs for these 3 tables. Okay, there is index move, table move, which is allowed online. Could be risky operation because there is only one transaction to do this. So you can have a huge BI file, huge after image file. I wrote about 6 times. It depends. It could be larger, smaller. Your management varies. The create update delete are not really allowed during this process. The result is not enough good for me because it depends on your index for the primary index key. If it's the same, you will have at the end a percentage util of 100%, which is good and bad, as you said, because you will split the index block each time you will add a new entry. If it's totally different, you will have a percentage util of 50%, which is extremely few little value. You have to index compact to be clean after this.
So speaking of IDX compact, so it's allowed online, fortunately. The process is, first we remove all the blocks that are in the RM chain, so all the blocks that are filled up only with index entry locks get recycled, and then you have a few iterations of compacting the blocks containing the non-leaf and the leaves. Since OpenH 12.6, there is an option on IDX Compact so that you can only remove the RM blocks, and it stops there. But obviously, you have limitations. So as you can see on my scheme, so I have put a red line to show the target ratio. And so you can see that blocks 1 and 2 are recycled, no questions asked. But the blocks 3, 4, and 5 are left untouched because the number of keys, so the percentage is above the target ratio. You have all those keys. And at this point, it doesn't matter if the keys are alive or dead. What will matter is the ratio, the amount of keys. So in our example, you have IDX compact that starts at block 6 and propagates for a few blocks. So at this point, we have removed index entry locks, but only because there was one point where we could start the treatment.
Okay, move back to my reads. So the question will be easy. When did I start my IDX compact? You can see it decreased a lot, and the read increase, but it's not the same ratio. You can read a lot of index for few records.
Right, so can we find tricks to make IDX compact work better in our case? So we were thinking about inserting dummy keys to force splitting of one block so that we generate at least 2 blocks that are about 50% in utility, so that IDX compact will start treating them and propagate for a few blocks, so you remove at least the index entry locks for a few blocks. So that was the idea. Doesn't work that way. If you try to, we found out that if you try to add records in a block that has a lot of index entry locks, before splitting, it checks if there are index entry locks and removes them so it doesn't split. Fair enough. It's also a good starting point for IDX compact because at least in our scheme we have reached utility percentage below our target, so it will be taken by IDX compact. And the good thing is that it doesn't matter which block you split. You can just force splitting any block, and it will create a good starting point for IDX compact. It's not very pretty, but it works.
Okay. The last good method is IDX build. Yes, but offline. After image deactivate, and if you have replication, you must reverse line. So it could cost a lot. So Progress is working on this subject. We create this idea, which is in progress. So we ask Progress if they could give us more information. They say you have to join CVP to know what's happened on this. So as part of CVP, you may get the opportunity to participate online and know what's happened on different IDs. So you may find what's happened or may not find on this idea. So, do you have questions?
Thank you for your attention. So if you have any questions, I'm sure you have. You can ask the expert.
Okay, so thank you.
Thank you.